Hey everybody, and welcome back, or if it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy. Spot my new light in the background, really happy with it. And this is all about learning networks together. That is what the Net Academy is all about. What we're actually going to concentrate on this video is more on this IS or intermediate system to intermediate system routing protocol. Now we're only going to actually cover two parts, two topics as such of this IS routing protocol in this video, and these are what are mesh groups and also the wide metrics. Now it may not sound like a lot, but there's actually a lot of detail that goes into these different areas, i.e. the mesh groups and the wide metrics. And as always, we're going to go through what they are, what do they do, what are the benefits of them, and of course how to configure that on the Juniper Junos devices. So let's go. And here we go. Here's the network itself. It's exactly the same network that I've been using for all the other videos I've done on this IS routing protocol. If you haven't seen them, look in the comments box. I've put the links to those videos that I've done down there, so feel free to check them out. But just as a high level, let's have a quick recap as to what you are actually looking at here, even if you have seen those videos. So what we are looking at is, of course, this IS network, this routing domain. And over here we have got area 1, we've got area 0 and area 2. Now area 0, just like OSPF, area 0 is that backbone, but a slight difference in IS is that the backbone doesn't need to be area 0, it could be something completely different. But just for simplicity and consistency, I've just named the backbone area 0. And what we've got are these different levels. Again, if you don't know the levels, just check out the other videos. But in this backbone that is area 0, everything is running at level 2. And when we look at area 2 over here, everything here is working at level 1. And when we look at area 1 itself, everything here is sort of like a mix between level 1 and level 2. So what does that actually mean? Well, if we look at it from an interface point of view, because we define the interfaces to be at a particular level, level 1 or level 2 or both. When we look at the interfaces in area 2, everything is level 1. So as I said, area 1, everything is area 2, sorry, everything is level 1. But when we look at area 0, and I said everything is level 2, we have level 2 here, we have level 2 here, level 2, level 2, level 2. And as you can see, there's quite a few level 2 connections there. But really, this is that backbone, as I said. I'm just going to do BCK for short. So it is that backbone. And level 2 will always have in its link state database, because this is a link state routing protocol, just like OSPF, we have got a link state database for level 1 and for level 2. And level 2 really has, unless you're doing any type of route filtering, it will have all of those entries in that level 2 link state database, level 1 inside of level 2. But let's look at area 1, where I said everything in here is almost level 1 apart from one exception, and that is the interface between routers R2 and R3. So the interfaces between R2 and R3, they are both level 1 and level 2. Level 1 and level 2. Whereas the interfaces from R2 and R3 to router R1, they are level 1 only. So I know that's made the screen quite interesting to look at, but just so you got a rough idea of the actual configuration. Oh, I missed a level 1 over there, but you get the idea. So really, this is the network setup. That backbone, area 0, everything's level 2. We've got everything in level 1 in area 2, and in area 1, most of the interfaces are level 1, except of that interface between routers on R2 and R3, where it's both level 1 and level 2. So I'm just going to clean up the screen a little bit. And now let's move on to this concept of mesh groups. And the reason why I talked about these levels is because of this particular reason. Now when we remember that rule set, and again, if you don't know what the rule set are or is, please refer to the other videos that I've done. But basically, every level 1 route, network, etc. will, unless you're doing any type of route filtering or firewall policies, etc., it will go into that level 2 link state database. But when we're talking about level 2 into level 1, this doesn't happen. By default, what actually happens is these ABRs, which are here, 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 and here, so just like OSPF, they are bordering different areas. So R2, R3, R6, and R7 are all ABRs. What they will actually do is inject a default route into that non-backbone area, i.e. area 1 and area 2. I'm basically saying I am attached. I'm flipping my attached bit here so that you know if you want to go to any network that is outside of this area, you can go through me because I have advertised to you this default route. That's ISIS for you. That's the default behavior. But as I said, everything that happens in level 1 is automatically populated by default into level 2, into that link state database. And we've got link state database for level 1 and link state database for level 2. But what happens if a link goes down? Say this link between router R1 and R2. Or what happens if there's a new network that we advertise into OSPF? Well, what happens in that case is that yes, it will be advertised down here, and maybe this link's gone down, etc. And when it comes to that backbone, to area 0, that level 2 and its link state database, that network flapping, that network advertisement is going to be sent through here, down to there, up there, across there, up here, across there, down to there, and down to there. And you can actually see that's a lot of overlapping traffic. And if we just look at it from this router's perspective, it's really getting 2 updates for exactly the same thing. And there are cases where, 2 typical cases where this would actually happen. And I just said it. So when there's a topology change. So when there's a topology change, i.e. a link is flapping, it's a bad link, it's going up and down and up and down, that is going to cause those LSPs, those link state PDUs, protocol data units, to be advertised across that ISIS routing domain. And if you're in that router, or intermediate system I should say, speaking as if in third person, if that router is in area 0 in this case, i.e. level 2, it's going to be advertising and receiving a lot in this network diagram of this particular update from many different interfaces. The other time where this would actually happen, and I'm running out of space here, so I'm just going to write it up here, is when the timer runs out. By default with ISIS, the hold down timer is 1200 seconds or 20 minutes. So what that means is when a new network is advertised, this router here, this router there, etc. Every router that learns of that new network will hold that network prefix in its link state database for 20 minutes. And it will go all the way down, not to 0, but to something like 337 seconds. Why 337 seconds, I don't know. I'd have to look into more of the ISIS routing protocol. But when it gets down to 337 seconds, it's then expecting R1 in this case to update its link state database, send out LSPs and say, yeah, this network is still here, it's still live, it's still active. And this is where mesh groups come into it. And what mesh groups basically do is they limit that broadcast flooding area. It's not really broadcast, but more multicast, I should say. It's reducing that flooding in either scope. So instead of flooding out all interfaces within that same level for this topology change or for this timer being expired, the hold down timer, in a mesh group we are going to send an update to here and an update down to here, and this is going to send an update up to there and an update up to there. Now that might sound like the same thing, but what is different is that these routers here, they will not then send back an advertisement back to here, or this won't then do the advertisement back to there. Okay, so it's allowing this capability to limit that flooding of these updates throughout the entire network. So what we would do, And what we are going to do is actually configure two different mesh groups. Now, mesh groups are done at the interface level. So we're going to have a mesh group 1 here, and we're going to do another mesh group all the way over here for mesh group 2. So two different mesh groups. And if you're wondering, well, does an update automatically go from mesh group 1 into mesh group 2 and in the opposite direction? Yes, absolutely, that will still happen. The whole idea of a mesh group is that you're limiting that flooding of those updates going throughout the network, and any router that's received a link state update, I know that's an OSPF term, but that LSP, that update of the topology change or timer, it will not then re-advertise that same LSP to another IS, another router, if it's in the same mesh group. And here's my secure CRT. As you can see, I've just logged into it, so I'm just going to go into the command line interface, and I'm on router R1, and I just want to see, can I ping all the way across the network to router R8? It's loopback interface of 8888 basically. So let's do ping 8888, and you can see we've got full end-to-end connectivity. If I just do a quick show IS-IS adjacency, you can also see I've got adjacency to both router R2 and R3, and I can even do show IS-IS database, which is going to be a very useful command in this video. We're going to be going through that a lot. You can also see what contents it's got in its link state database. As you can see, it's not a lot, but from R1 it's not really connected to much, and we're not advertising much through it. But how do we actually configure those mesh groups? Well, as I just said and showed, we're not really going to do that on router R1 in area 1. We're actually going to do that on all the interfaces in area 0. So where is the configuration actually done for these mesh groups? Well, I gave away a little bit. These are actually done at the interface level, but within the actual protocol. So we have to go into protocol IS-IS and define the interface to be within a particular mesh group. So I'm going to do this for every single router just very quickly. So remember, we're going to do both mesh group 1 over here as you look at my mouse, and we're also going to do mesh group number 2 over here. So where do we actually configure the mesh group? I just did give it away a little bit. We actually do this within the interface level, but within the protocol. So we have to go within protocols IS within that interface to define that particular mesh group number. If you can't remember what those numbers are, just put it on the diagram. I'm not an artist, apologies, but just so you could see what interfaces on which routers are going to be part of which mesh group. So I'm on router R2 here, and I will just go into CLI mode, go to configure, edit protocols, IS-IS, do a quick show for us, and we can see the current configuration. Now, as I just said, I need to define the interface, so let's do set gigi 004, which is going to router R4, and we want to have mesh group number 1. That is it. That is how quick and easy it is to actually define a mesh group number. But that's obviously just a one interface for one router. We need to do that for all the other interfaces on the same router and on the other routers for really the benefit of this mesh group feature to come into effect. So now we'll do this for gigi 005 and gigi 003. I'll commit that and go to router R3. It's going to CLI configure mode, and I'm just going to do it right from the top. So set protocols IS-IS interface gigi 002 mesh group 1, and I need to do this to the same to router R4, R5, and I will commit that configuration. And let's go to router R4. Now we need to remember here that we've got two different mesh groups, mesh group 1 for some interfaces and mesh group 2 for some other interfaces. But nonetheless, we need to go into configure mode, CLI mode, and then go into configure, and let's do set protocols IS-IS interface gigi 002 mesh group number 1. And now I need to do the same for the gigi 003, which goes to router R3. But now I'm going to do mesh group 2 for the gigi 006 interface and the gigi 007 interface. I'll give that a commit there, and we have now just configured two different mesh groups on router R4, mesh group 1, mesh group 2. Again, need to do that on the other router though, so let's go into CLI configure mode, set protocols IS-IS interface gigi 002 mesh group 1, gigi 003 mesh group 2 out of the gigi 006 interface, and gigi 007, commit the configuration, and finally, well, penultimately I should say, let's go into the CLI mode and configure on router R6 is do set protocols ISIS interface GigE004 mesh group 2 GigE005, commit the configuration, and now lastly router R7 command line interface configure mode set protocols ISIS interface GigE004 mesh group 2 GigE005 and commit to that configuration. So I know there was quite a few routers there and quite a few interfaces, but you really got the idea, and repetition is always a good thing if you want to learn this. That is how quick and easy it is to configure a mesh group on Juniper Junos. All you have to do is go into, yes, the protocol ISIS, but to define that interface to be level 2 or level 1 disable, etc. But mesh group 1, mesh group 2, whatever it may be. And then, because we've done that, these routers here, so if R2 is advertising up to router R2 a particular network change or a timer, R4 is not going to send that update out of the interface here or over to R5 if you add an interface there. What it would do though is it would still send that topology change or that update through mesh group 2, and thus this whole network stays intact. And to put that into a working scenario, if I come back to router R1, can I still ping all the way from router R1 to router R8? So let's just do run ping 8888, and we absolutely can. So from router R1 it doesn't really see any difference, and without doing a Wireshark and all these different interfaces in area 0 in that backbone, you're not really going to see if there was a topology change or a timer expiring. You're not going to see the benefits, but that is what mesh groups do, is they limit that broadcast, so that flooding of all those updates going in and out of the interfaces, and thus they control all that traffic and reduce those CPF calculations, etc. that has to go through when we're talking about link state routing protocols such as ISIS and OSPF. But now let's actually move on to metrics. Now, as we know with OSPF, and if you don't know OSPF, check out the OSPF videos I've done. Here's a quick link, or just go into my other videos that I've done. But the cost for OSPF is based on this simple algorithm, this simple calculation, where we've got a reference bandwidth, and that is divided by the interface bandwidth. And you can change the reference bandwidth here, you know, something like set protocols OSPF reference bandwidth and whatever that value might actually be. But in the ISIS world it is slightly different. We don't actually do this in the ISIS routing protocol. By default, every interface will have a cost of 10. By default, it doesn't matter how many links are in between routers R1 and R8. We've got one here, and we've got one here, and one here, and one here. And if this is a cost of 10 plus another 10, we've got 20, we've got cost of 30, and then a cost of 40. It doesn't matter if this was a GigE and this was a fast Ethernet, etc. By default, everything's going to have a cost of 10. And I know what you're thinking. You're thinking, well, hang on, stop, Dave. You said everything at the beginning would go out with a 00.0 default route. Yes, absolutely, that's still true. That's why I said if you were doing some kind of route leaking where you would actually leak out that 8888 loopback interface into router, into area 1 from that backbone area 0. But yes, by default you would have that default route. But here and here you'd still have this cost of 20 or 30 regardless. This could be 100 gig, just for example. It's still going to have that default cost of 10. So if we actually put that into practice, I've just logged on to router R2 up here, and this actually just do, from the configuration mode, just actually do run show ISIS database. And here we can actually see, let me just maximize this a little bit more. And here we can actually see the link state database for link state database 1 and for, or level 1 I should say, and the level 2 link state database. Now we don't actually see 888 here. What you do have to do, and I'll come back to as to why I actually show this just in a second, but what I will do is just do run show ISIS route. Now what we can see now is that 8888/32. Note the cost or the metric is that of 30. Why is it a cost of 30? Well, again, from R2's perspective, it's really got two paths open to it, two egress interfaces to get to router R8. It can go out the GigE004 interface or out the GigE005 interface. And in either case, it's got 10 here, say 20 there, and then 30 there. So why is it a cost of 30? Well, again, as I explained, the default cost for ISIS is 10. We can change this, of course, but if we look at it from R2's perspective, it knows to get from here all the way over to router R8, it's only got two interfaces, two egress interfaces available to it. It can go out the GigE 004 interface or out the GigE 005 interface. And in either case, it just knows I've got one link here, and this is advertising, it's got a cost of 10, and this router is advertising, it's got a cost of 10, so we've got 10, 20, 30, and if we go out the other interface, GigE 004, we know it's a cost of 10 here, another cost of 10 there, so it's 20, and another cost of 10, i.e. 30. This is how just a link state routing protocol, the SPF algorithm, just generally works. But if I come back to that command run show ISIS database, then what I want to look at is the level 2 link state database. And you can actually see there's quite a few different entries for really the same router. So we could see there's only one for router R2, there's 2 for R3, there's 2 for R3 for R4, etc. There are different reasons for this. So just quickly, the R4000, this is where it is defining it as an intermediate system. So this is R4 itself. However, the R40200 is where you would have a designated intermediate system, or in the OSPF world, that would be the designated router. In the ISIS world, it's called a pseudo node. So in here would be the actual designated router advertising the details, the link state PDUs for R402, i.e. the designated router 00. So these different LSPs do have different meanings to them. But I want to look at R5, and I want to look at the intermediate system itself, so I'm going to do R500-00, and let me just do detail here. And what we can actually see are all the different neighbors, so we can see who's connected to router R5, and we can then see the extended IP prefixes, so the basically networks that are connected to router R5. And note here the cost. Now we can see a cost of 10 here and a cost of 10 here, and using this information just like we do in the OSPF world with the link state advertisements, specifically those link state updates, here we know in that OSPF link state database, just like we do in this ISIS link state database, we're basically building that topology, we're building that tree and understanding who's connected to who, what metrics do they have advertised to and from each other, and thus it's able to calculate using that Dijkstra algorithm what is the shortest path to get from source to destination. So what is the kicker here? Well, in this backbone, which is area 0, you could see everything is running at 1 gig. Now in reality, depending on the size of the network, not many of those interfaces would be running at 1 gig. You might have 10 gig here, or even 100 gig here. Up here could be 40 gig, and then you could still have 1 gig here, and this could be 100 gig there, etc. But it doesn't really matter, because the default in ISIS is to always use a cost of 10. And as such, what could happen if this was lower, if this path here was lower cost, just for example, and as such it wouldn't do load balancing over the available links. If it took this path here, it would actually be doing suboptimal routing, because it's taking that interface which has less bandwidth available to it, versus then going via the more optimal path that has 100 gig actually available to it. Now if you know our OSPF, you actually be very, very familiar with this command where you can actually change this. And the command is very easy. It is set protocols ISIS reference bandwidth, hit question mark, and then you basically define what is the bandwidth. So here I'm just going to say 100 gig. And if I just do show protocols ISIS, we can now see that I've entered in that reference bandwidth of 100 gig right here. Now that is just for router R2. You have to do that for every single router throughout that ISIS routed domain for this to really take sense and to really leverage, you know, the capabilities, not just to use that default of 10. But let's do a commit here. Let's go into router R3, do the same command, and I'll commit on R3. On R4, set protocols ISIS reference bandwidth 100 gig. Commit. R5, set protocols ISIS reference bandwidth 100 gig. Commit. R6, set protocols ISIS reference bandwidth 100 gig. Commit. And finally on R7, set protocols ISIS reference bandwidth 100 gig. Commit. And that is R7 configured. That's all the routers actually configured. I've even done R8 just very quickly, but that's how easy and quick it is to configure and change that default behavior of ISIS. Whether it be Cisco or Juniper, doesn't matter. This is the default behavior. Every interface will have a default cost. On Juniper Junos it is 10. It might be different for other vendors, but it is going to have a default value or cost or metric associated to it. So let's go back to router R2. And let's actually run that same command now. So if I do run show ISIS route, so I want to see and show the routing table for all routes learned by the routing protocol ISIS. And now we can see, we don't just see 10, 20, 30, 30, 30, etc. Now we actually see 63, 63, 63. And for the 8888, so this is from R2 to get to router R8, it has got a cost of 189, sorry. So if I actually just do a little bit more detail into that, so I'm going to do run show ISIS route, I'm going to do 8888/32, I'm going to give the detail behind this. And we can see a little bit more detail as you would expect, but if I actually just do extensive, just to show you the difference in commands. And you learn something new every day. There's not actually an extensive for the ISIS route, but it is actually for the database, so I can't do that. But if I just do detail again, what we can see is that it's going to use the outgoing interface of Gigi 004, so that is going to router R4 up here, sorry, and that's got a cost of 189. So it knows, R2 knows, to get from here all the way over to here, it's going to cost me 189. But there's something running here in the background which you will not be aware of. And just to put that into a bit more perspective, I just do a run show ISIS database. I know we've seen this a few times, but as I said, this is where we're going to be spending a bit more time. So I want to look into more of this link state PDU ID, i.e. the IS system itself, router R4. So I'm going to run that same command again, but now I'm just going to do R400-00, and I want to see the detail behind this. Now, this is what's running in the background. We have got what is called our narrow metrics. These are the narrow metrics right up here. The IS neighbor, etc. These are the narrow metrics. But then we've also got our extended prefixes. Now, if you don't know what these are, here's a little bit of maths for you. I say a little bit of maths, it's also a little bit of history. But these narrow metrics, these are using a TLV of 128. So it's a type length value which has a type of 128. So if you see a packet with a TLV and the type 128, you know it is defining a narrow metric. But regardless of that value in there, well, not actually regardless, that value within here is always going to be a maximum of 63. And we actually just saw that in that link state database. We saw it on a few entries, 63. And this is important because in these narrow metrics, with that TLV of 128, it was only limited to 6 bits. What you come out with is actually 64. However, we've got to remember that 0 is actually a number, and thus it is 0 to 63. So the point here being is that even if this was 100 gig here and another 100 gig here, or even 1 gig here, and etc., we're only going to ever have a cost of 63 here, and another cost of 63 here, and at max another cost of 63 here. That's as maximum as it's ever going to go. So this was actually updated within the different standards to make ISIS a little bit more modern and a little bit more flexible in its approach. And this is what's known as the wide metrics. And with the wide metrics, we are still using TLVs. ISIS loves TLVs. It's what makes it so incredibly flexible and scalable and future-proof. And there are actually 2 different TLVs. We use types 22 and type 135. Now, the difference between these, I would have to look it up, to be honest. But what I do know is that it now defines 24 bits. Now, that might not sound like a lot more, but if you were to do 2 to the power of 24, you would come out with 16,777,215. So the maximum metric and cost that can be associated to any path can be up to that maximum. So that is a lot better than 63. Now let's actually put this into practice. What I'm going to do is I'm going to log on to router R4 and I'm going to change the Gigi002 interface to have a lot higher metric. I want this not to be preferred by router R2. So let's log on to router R4 and let's go into Edit Protocols, ISIS, do a quick show, and we can see we've got all the configuration that we have done so far, the mesh group, the reference bandwidth, etc. But what I want to do is I want to increase that metric. So what I'm going to say is set interface Gigi002 level, we have to define the level 2 metric, and I'm going to give this a metric of 1000, just for example. And now if I commit this, so with that committed now you can see it's completed, and I can just show it here. So we've got the level 2 metric of 1000 going out the Gigi002 interface. So if we go on to router R2, what we should see between routers R2 here and router R4, it should have surely within that ISIS database and even that ISIS route that cost of at least 1000. So let's actually see this. So if I do show nearly run show ISIS database just to refresh, and I want to look at R4, the intermediate system itself. So let's run that same command again, but now I'm just going to say R400-00 and I want to say detail. We can still see it is only 63. So the metric to get from R2 to R4 is still 63. Why is that? And that is because by default, again, just like the default cost of 10, and there's some things running behind the scenes here that you do need to change. It's only one command, but Junos will first look at the non-extended IP prefixes. First it will look here and it will use those narrow metrics. It's just what's enabled by default. So what we have to do to change this so we can actually see more realistic figures, so we can actually see that cost of 1000 here instead of 63, because that's what the narrow metrics are limited to. Don't forget, 6 bits, you're only ever going to get to 63, so we're not going to see the huge metric of 1000 here. It's way past 63. We need to go into every router now and enable the wide metrics. Now to do so, it is very straightforward. All you do is set protocols ISIS and you define the level. So here, because I know I want it to go out the level 2 interfaces, I'm going to say level 2 wide metrics only. That's it. Hit commit, and we have to do this on router R3. So set protocols ISIS level 2 wide metrics only, commit. R4 wide metrics only, commit. R5 level 2 wide metrics only, commit. R6 level 2 wide metrics only. R7 set protocols ISIS level 2, I keep doing that, wide metrics only. I'll commit that, and I will also go on to router R1 and do, I don't have to do it because it's only going to see the default route anyway, but I'll do set protocols ISIS level 2, keep doing that, level 2 wide metrics only, and I'll hit commit. And that's it. That's how we actually define the wide metrics. So now Junos is going to be preferring those TLVs 22 and 135, where we can have a maximum of 16,777,215 cost or metric for any given route versus 63 per hop. It's just not realistic, and now we're going to see that impact on the routing table and of course that link state database. So with that committed on R7, let's now go back to router R2. Let's run that same command and see, has it actually changed? So here we are on router R2. I'm just going to hit up, and there we go. Run show ISIS database, and I want to go into the detail of that intermediate system router, that is R4. And there we go. Straight away, by using the wide metrics, we can now see higher than 63. So we can actually see to go to that intermediate system, router R4, it's going to cost me 1000. That's great. We've now moved away from the narrow metrics, which are always going to be limited to 63 per hop, which will then derive that interface cost, that metric, going along that path to that destination. We are now going to see, just to get to router R4, it's going to cost me 1000. That is absolutely going to impact the decision making process, what goes into the packet forwarding table from the routing table, well really from the link state database into that routing table, in terms of what path will R2 take to get to router R8? Is it going to go through router R4 or will it go through router R5? And there we go, everybody. That's the end of this video. I hope you found that useful and informative. So I want to do a quick recap. First, on the mesh groups, what are the benefits of those? It essentially stops that flooding. So when a router's interface receives from the same mesh group router a update via the LSPs, it will then not forward that update to another mesh group peer. It won't do it, and that is then having a significant impact on all those packets going through the network. So instead of overlapping packets going in every single direction in my network, by using those mesh groups, mesh group 1 and mesh group 2, we've limited that flooding scope, but we have still enabled those updates to go from mesh group 1 to mesh group 2. R1 and R8 can still ping each other, of course. That is mesh groups, and as we saw, incredibly quick and easy to set up. Set protocols, ISIS, interface, the interface of course, and then you go mesh group number. That's it. We then went into metrics, and that's why I said at the beginning of this why this is actually a big topic, because there's a lot of defaults that the ISIS routing protocol actually uses, i.e. the default cost is 10. So it doesn't matter if you've got a 1 gig of fast Ethernet or 100 meg or 2 meg pipe running between routers, that cost is absolutely always going to be 10. Now that's obviously not ideal. So we went through why that is actually the case, and when we actually enabled that reference bandwidth of 100 gig, it then increased to a maximum of 63 because we changed that reference bandwidth, so moved away from that default of 10. But that then is limited to that default behavior on ISIS of those narrow metrics. Within that TLV of 1 to 8, you've got 6 bits, so you're only going to have a maximum of 63 per hop. Obviously that will increment with the more hops, but this is a link state routing protocol, not a distance vector routing protocol. But we saw that on the routing table and the ISIS database that it was only limited to 63 or 126, etc. It's incremental. But then we saw when we enabled within the ISIS level wide metrics use only and jacked up that cost on the R4's interface, how then we were able to get more realistic and more modern and more trustworthy metrics and cost instead of that default behavior. So I hope you found that informative, a lot of information. If you like this video, please give me a thumbs up, please subscribe, please give me your comments. I'll do my best to answer them. I do love hearing from you guys. I know you're finding this content useful. Stay tuned for the next video where we're actually going to start talking about route leaking, i.e. when we take a route, a network that is learned in that backbone area 0, and how we can actually import that into that non-backbone area, and a little bit more information as well. So thanks for watching. See you later. Goodbye.